the universe from nothing, the quantum loophole that created everything. There's a moment we can't photograph, can't even imagine clearly, the instant before everything began. No galaxies, no particles, no time. Just a void with no stage, no actors, yet somehow destined to explode into existence. That's the paradox at the center of everything we know. How can something arise when there was nothing there to begin with? For most of human history, that question belonged to philosophers and theologians. It was too grand, too absolute for science. But then the math started whispering secrets. When physicists extended quantum theory to the edge of space-time, they found that nothing might not be the barren emptiness we thought. At the tiniest scales, fluctuations appear spontaneously, blips of energy, winking in and out of being. What if the whole universe is one of those blips, stretched and magnified beyond all recognition? It sounds impossible, yet pieces of evidence line up with unsettling precision. The patterns in the cosmic microwave background, the way galaxies drift apart faster and faster, the faint hum of dark energy pressing outward on the fabric of space itself. All of them trace back to an origin that should have been impossible. The universe behaves like a miracle disguised as physics. Now here's where it gets even stranger. According to quantum mechanics, the rules don't forbid something from emerging without a cause, so long as the books balance. A tiny fluctuation can appear as long as positive and negative energies cancel each other out perfectly. Matter on one side, gravity on the other. It's like the universe borrowed energy from itself and owes exactly zero debt. A cosmic loophole hidden inside the uncertainty of nature. But there's more at stake here than equations. The idea cuts deep into our sense of meaning. Physicists such as Lawrence Krauss and Stephen Hawking claim that no external creator is required, that the laws of quantum physics alone can produce a universe. Philosophers push back, saying that a vacuum filled with laws and fields isn't nothing at all. It's a very specific kind of something, dressed up as emptiness. That clash between empirical law and existential wonder didn't start in a lab. It began the moment we asked the simplest and hardest question: why is there anything here at all? And now science, armed with telescopes and particle accelerators, is circling that same mystery from a new angle. If physics can show that nothing must fluctuate, maybe the act of creation isn't an exception to the rules but a direct consequence of them. Still, the deeper we look, the less solid nothing becomes. Within the equations, emptiness seethes with invisible energy. Even the calmest vacuum hides restless ghosts of particles that flicker into being and vanish before they can exist for real. Each event is fleeting, random, yet relentless. And at that scale, before atoms, before light, before time itself, every possibility is technically allowed. In the right conditions, those quantum tremors could inflate into an entire universe. But here's the haunting part. If that's true, then the origin of everything may not carry any grand purpose at all. It might be just one quantum roll of the dice. And yet, that random act produced galaxies, stars, and us, the storytellers trying to reverse engineer our own beginning. So tonight, we're diving into that loophole, the quantum quirk that may have given birth to spacetime itself. We'll trace how Einstein's equations accidentally hinted at it, how modern physics wrestled with its consequences, and how philosophers refused to let the word nothing lose its meaning. Because somewhere between those arguments, between fields, constants, and the silence before creation, lies the strangest possibility in science: that the universe didn't start with a bang of divine intent, but with a whisper from the vacuum. And if that whisper still echoes, it means nothing never truly ended. It transformed into everything we see. The human obsession with origins. Every culture at some point has stared into the dark and asked the same impossible question: why is there something rather than nothing? You can find it carved into stone myths and whispered through creation hymns. The ancient Sumerians spoke of the god Namu, born from the primeval sea, shaping heaven and earth out of formless chaos. The Greeks imagined Gaia rising from the void. In the Rig Veda, creation was born out of a cosmic breath. Each story tried to tame the restless fear that maybe there could have been nothing at all. Because nothing doesn't just mean emptiness. It means no memory, no story, no one to tell it. Centuries later, we still circle that same question, only now our gods have equations. Yet the emotion behind it hasn't changed. When early humans looked up at the stars, they weren't doing physics. They were trying to understand why there was something to look at in the first place. The night sky was both proof and mystery, glittering evidence that the universe exists, but also a reminder that we don't know why. As civilizations advanced, creation myths became cosmologies. The Babylonians mapped the heavens to track seasons. The Egyptians built celestial order into their pyramids, and philosophers from Aristotle to Aquinas turned creation into logic. Each believed the universe had an underlying reason, a cause or a purpose that made its existence necessary. Aristotle called it the unmoved mover, the first cause that sets everything else into motion. It made sense emotionally. Nothing moves without being moved. Something must have flicked the first domino. For nearly 2 millennia, that reasoning held fast, refined by thinkers like Aquinas and echoed through theology and early science alike. But in the early 20th century, the quiet faith in a stable cosmos met its unexpected challenger, not through revelation but through mathematics. When relativity arrived, it split the sky open. Space and time themselves were about to move. The obsession with origins didn't fade, it evolved. During the Enlightenment, astronomers started to replace mythic timelines with celestial mechanics. Newton showed that gravity held the solar system together, that precise laws governed the heavens. But he left one question untouched. Where did those laws come from? He called them the workmanship of a divine power, a careful hedge between science and scripture. For a while, that balance worked. Science could describe the cosmos without explaining its birth. Then came the 20th century and the comfort evaporated. Telescopes grew stronger, mathematics reached further, and Albert Einstein rewrote how we measure time and space. Suddenly, the universe wasn't fixed or eternal. It was a fabric that could warp, stretch, and expand. The sky wasn't static at all, it was moving. That discovery blew apart the ancient idea of a timeless cosmos. If space was expanding, logic demanded that once upon a time it had been smaller, far smaller. Maybe infinitesimally small. The question of origins turned into a question of physics. By the mid-20th century, the idea of a Big Bang had taken hold, a moment when the universe burst outward from an infinitely dense singularity. Scientists didn't yet know what triggered it or what existed before. Some said nothing did. Others said time itself began there. But one thing was clear: creation had transitioned from a divine act to a physical event. And that shift didn't make the mystery smaller, it made it stranger. Because even as cosmology advanced, the emotional pull of the question never loosened. People wanted to know not just how it happened, but why it happened at all. When scientists said the universe came from a fluctuation, the public heard a different kind of miracle, one disguised in scientific language. Was that fluctuation inevitable, random, meaningless? Those questions sit beyond the reach of telescopes, but they still keep people awake at night. Psychologists would later argue that this obsession is built into us. Human minds hate uncaused events. We see patterns where there are none, invent motives for every noise in the dark. It's a survival trait that became philosophy. We crave answers that connect dots from beginning to end. A universe from nothing destroys that instinct. It's a story with no storyteller. And that contradiction gnaws at us. How can there be consequence without cause, meaning without a source? Still, each leap in understanding made the original question more compelling. The 192s saw Edwin Hubble prove that distant galaxies were receding. The farther they were, the faster they moved. The universe was expanding, and by running time backward, scientists could trace everything back to a single origin point. It wasn't myth anymore. It was measurement. But even as the math got sharper, so did the doubts. If the laws of physics describe everything inside the universe, what describes the moment those laws themselves began? Did the laws exist before matter? If so, in what sense? And under what clock? Throughout history, the search for origins mirrored our deeper insecurities. Every theory of beginning was also a mirror for human fear. Fear of impermanence, fear of randomness, fear that our story might not matter. Maybe that's why this topic endures across cultures. It isn't just about physics or philosophy, it's about identity. If everything came from nothing, then we are fragments of an accident. If not, then we're part of an intention grander than ourselves. Either answer is unsettling. In modern classrooms and observatories, we rarely mention the emotional side, but it lingers quietly behind every diagram of the early cosmos. You can feel it when scientists describe background radiation as the afterglow of creation. Even in the cold language of data, words like birth, origin, and horizon betray our awe. We don't just want to solve equations, we want to understand our own meaning within them. And so, the story of something from nothing has never been just about physics. It's about imagination. Humanity's oldest instinct is to look backward from the present and ask, what came before? That's why this question endures even when it seems unsolvable. It binds mythmakers, poets, and astrophysicists together. Every generation tries again, drawing the line of causality further back, daring to ask what lies beyond the first instant. But we've reached a strange point in that journey. The closer science gets to the first moment, the more elusive the answer becomes. Time dissolves into probability, matter into fields. The difference between something and nothing starts to blur until the words lose meaning. And yet in that blur we keep searching, because curiosity and fear are two sides of the same spark, the spark that might have ignited the universe itself. To understand how we reached this point, how the question shifted from myth to mathematics, we need to look back once more, to the moment when even the idea of a static universe was challenged by one man's reluctant equation, a symbol he introduced, regretted, and that would later turn out to hold the secret code of cosmic expansion. Einstein's reluctant constant. When Albert Einstein published his general theory of relativity in 1915, he thought he'd found the ultimate description of gravity. Space and time weren't passive backdrops anymore. They were flexible, dynamic, bent by mass and energy. But soon after presenting his theory, Einstein faced a problem he didn't expect. His equations implied that the universe couldn't stand still. The cosmic fabric would either stretch outward or collapse inward. That wasn't what anyone, including Einstein, wanted to hear. At the time, astronomers and physicists assumed the universe was static and eternal. The stars, they thought, had always been there. The idea of cosmic change seemed absurd. So Einstein did something daring for a man known for intellectual purity. He modified his own theory. He added an extra term, a mathematical cushion, to counterbalance gravity's pull. He called it the cosmological constant, represented by the Greek letter lambda. In essence, lambda acted as a kind of anti-gravity. It pushed outward just enough to hold the universe steady against the inward tug of mass. With that addition, Einstein's equations described the tranquil, eternal cosmos everyone expected. He was satisfied, at least for a while. He even called it the most natural form of the equations. But nature had surprises waiting. About a decade later, Edwin Hubble used Mount Wilson Observatory's new telescope to measure the light from distant galaxies. He noticed that their light was stretched toward the red end of the spectrum, a sign they were moving away from us. The farther a galaxy was, the faster it receded. The universe was expanding. Suddenly, Einstein's static model looked obsolete. According to later recollections, he reportedly muttered that introducing the cosmological constant had been his biggest blunder. He removed it from his equations and moved on. For decades afterward, physicists agreed that lambda was unnecessary. They treated it as a mathematical relic, a patch on reality that didn't need patching. The Big Bang theory gained momentum, describing a universe evolving dynamically from a hot, dense beginning. That seemed to close the book on Einstein's constant, but the universe wasn't finished with it. In the late 199s, teams studying distant Type Ia supernovae, the universe's exploding stars, made a jolting discovery. Those supernovae were dimmer than expected, meaning they were farther away than they should be if cosmic expansion were slowing down. The universe wasn't just expanding, it was accelerating. Something invisible was pushing it apart faster and faster. When scientists fed that data into Einstein's equations, the only way to make the math work was to bring back the cosmological constant. Just like that, the blunder became indispensable. That outward pressure became known as dark energy. Today, it's thought to make up roughly 70% of the total energy in the cosmos. It doesn't clump or radiate, and it doesn't interact with light. It simply exists as the energy of space itself, driving everything apart. And our best measurements match what a constant lambda would do: produce a steady, small acceleration that grows more obvious over billions of years. The irony runs deep. Einstein added lambda to hold the universe in a static balance. In reality, it appears to be the engine of cosmic expansion. The same symbol he tried to remove may define the destiny of everything. If lambda remains truly constant, galaxies beyond our local neighborhood will drift forever out of reach, leaving an empty, cold sky. But if lambda changes over time, as some new theories propose, the future could be stranger still, oscillating between slow and rapid expansion, or even ending in a big rip, where space itself tears apart every atom. The cosmological constant raised another question Einstein couldn't have imagined. What exactly gives empty space its pressure? According to quantum field theory, even a perfect vacuum seethes with energy. Every field, electromagnetic, Higgs, gravitational, vibrates with virtual particles blinking in and out of existence. Add up all those contributions, and the vacuum should have enormous energy, enough to curl spacetime into a tiny ball. But the real universe expands gently, not violently. The predicted energy is outrageously too high, about 10,120 times larger than what observations show. No other calculation in physics misses by that much. It's been called the worst theoretical prediction ever made. That mismatch is what physicists call the cosmological constant problem. It forces them to ask whether there's some hidden mechanism that cancels most of that vacuum energy, leaving only the faint residue we see as dark energy today. Some suspect it's a matter of symmetry. Others think new physics, maybe quantum gravity, will reveal the fix. Whatever the cause, it suggests that our understanding of empty space is deeply incomplete. Einstein's harmless add-on turned into a gateway between gravity and quantum mechanics, the very frontier physicists still can't unify. In his time, the constant was pure mathematics. Today, it's an open invitation to reconsider what nothingness actually means. When cosmologists talk about the vacuum energy behind lambda, they're talking about the restless heart of nothing itself. Meanwhile, observations keep refining the picture. Surveys like the Dark Energy Survey, the Dark Energy Spectroscopic Instrument, and satellite missions from Euclid to the upcoming Rubin Observatory continue scanning millions of galaxies. Their goal is to chart how cosmic expansion changed over billions of years. If lambda has varied even slightly, those programs could catch it. Some data already hint it might not be perfectly constant, perhaps a field that evolves slowly with time. If confirmed, that would mean dark energy isn't a true vacuum property, but a dynamic phenomenon intertwined with cosmic history. Standing on this crossroad between relativity and quantum physics, Einstein's constant feels less like a mistake and more like a clue, a faint fingerprint of deeper laws. It connects the geometry of space-time with the tremors of the quantum vacuum, linking the very large to the very small. Without realizing it, Einstein built the doorway to questions he never got to ask. There's a trace of humility in that. The man who tamed the cosmos with equations still stumbled when faced with its ultimate balance. He admitted it freely, yet his error keeps shaping the course of science. The cosmological constant reminds us that even missteps can contain deeper truths waiting to unfold. Each correction drives us closer to the boundary where simple models collapse and reality begins to whisper through the math. And so, what began as a reluctant adjustment became the backbone of modern cosmology. It tells us the vacuum between galaxies isn't truly empty. It's alive with a gentle pressure that dictates the universe's fate. But that discovery only deepens the mystery. Because if empty space can push the cosmos apart, then emptiness has energy, and energy means substance. Which leaves us with a new problem. Maybe nothing isn't nothing at all. That's where the story turns next, to the strange idea that the vacuum itself buzzes with invisible power, a restless sea that makes up most of reality. The next step is to look closer at that space between stars, that seeming void where creation never really stopped. The vacuum that isn't empty. It sounds like a strange contradiction, an empty space that's full of something. But that's what modern physics tells us about the vacuum. It isn't empty at all. What looks like nothing, even in the deepest corner of intergalactic space, is actually an ocean of activity. A region stripped of particles still contains the quantum fields that define everything, and those fields refuse to sit still. In the old Newtonian sense, a vacuum was simple. You removed all matter, all air, and you had nothing left, a pure void. But when quantum field theory came along in the 20th century, it rewrote that definition. According to this framework, every type of particle corresponds to a field spread throughout the universe. Electrons, quarks, photons. They're not just objects but excitations in their own fields. Even when those fields are in their lowest possible energy state, they fluctuate. Tiny wiggles appear and disappear too quickly to notice. The average looks calm, but underneath, there's constant motion. These restless ripples create what's called vacuum energy. It's a kind of background hum, measurable only through its effects. One famous example came from experiments like the Casimir effect, where two metal plates placed extremely close together feel an attractive force, even though no actual particles are between them. That pressure doesn't come from air or heat. It comes from the quantum vacuum itself. The space between the plates has slightly fewer modes of fluctuation than the space outside, creating an imbalance that pushes them together. It's reality revealing that nothingness has weight. Now scale that up to the entire cosmos. The vacuum energy fills every cubic meter, contributing an invisible density to space. In quantum field theory, all those fluctuating fields add up. Each vibration carries energy, and when you sum them across every possible frequency, the result is absurdly large. Depending on how you set the cutoff point, somewhere around the Planck scale, the theoretical energy density of the vacuum could be 10 to the power of 120 times greater than what we actually observe. That number isn't just wrong, it's catastrophic. If it were true, the gravitational pull from that energy would have curled the universe into a microscopic bubble long ago. Galaxies, planets, even atoms couldn't exist. Yet here we are, and the observed vacuum energy is incredibly small but non-zero, just enough to accelerate cosmic expansion. This mismatch between what quantum theory predicts and what telescopes measure is the most dramatic discrepancy in all of science. Physicists call it the cosmological constant problem, and it sits right at the boundary between quantum mechanics and general relativity. Relativity treats energy as a source of curvature for spacetime. If empty space has energy, its gravitational effect should be enormous. But for reasons we don't yet understand, most of that energy seems to cancel out. Some unknown mechanism, perhaps a symmetry we haven't discovered, reduces the vast theoretical value to the minuscule level that fuels dark energy today. When people hear the phrase vacuum energy, it might sound like speculative science fiction, but its fingerprints are everywhere. Without those fluctuating fields, atoms wouldn't behave the way they do. Even the stability of matter depends on these background jitters. Virtual particles appear for a blink of time, interact, and vanish again, never directly observed but influencing measurable quantities like energy levels and electromagnetic forces. The word virtual doesn't mean imaginary, it means ephemeral, existing within the limits allowed by the uncertainty principle. That principle lies at the heart of it all. Quantum theory forbids exact stillness. Position and momentum, or energy and time, can't both be precisely defined. The vacuum must fluctuate, otherwise the uncertainty equations break. So even when a field is empty, it borrows energy for an instant, sprouting pairs of particles and antiparticles that annihilate almost immediately. It's this spontaneous borrowing that hints at creation itself. To picture it, think of spacetime not as a flat void but as a restless sea. Most waves cancel out. Some converge briefly to form larger crests, and then everything levels again. Each crest is a virtual event, short-lived, balanced by an equal and opposite trough. On average, the sea is calm, but its potential is immense. A fluctuation on a cosmic scale could, in theory, seed an entire universe if it escaped cancellation. That idea sits at the bleeding edge of cosmology, suggesting the universe might have begun as a quantum fluctuation too large to fade away. But let's slow down. First, we have to accept what's already proven. The vacuum, by every test we can design, possesses structure. Quantum chromodynamics, the theory describing strong nuclear force, shows that even empty space is filled with gluon fields and quark condensates popping in and out of existence. The Higgs field, responsible for giving particles their mass, pervades all space even where no particles are present. In other words, the universe's supposed emptiness is actually the most crowded arena imaginable, crowded with possibilities rather than people. This discovery reshaped the philosophy of nothing. Before the quantum era, nothingness meant absence. Now it means potential. It's the ground state from which everything emerges, alive with statistical chance. The void became a stage that never closes. When cosmologists compute the energy density of vacuum space, about 5.36 times 10⁻10 joules per cubic meter, they're measuring the energy of nothing. Multiply that by all the space in the observable universe, and the amount becomes staggering. We exist inside a limitless energy reservoir we barely understand. That realization forced theoretical physicists into uncomfortable territory. If the vacuum defines energy, does it define reality itself? Could properties like space, time, and inertia all be emergent effects of these fields? Some experiments now test that line of thought. They look for subtle variations in how light moves through supposedly empty space, or how gravitational waves might interact with vacuum fluctuations. Every test so far supports the same unsettling truth. The vacuum behaves like a physical medium with its own pressure and tension. Still, one mystery persists: why so little energy survives. Some models suggest positive and negative contributions from different fields largely cancel each other, leaving a small residue proportional to the cosmological constant. Other approaches imagine that vacuum energy runs with cosmic expansion. As the universe grows, the vacuum adjusts, keeping its density roughly stable. These running vacuum theories aim to ease the fine-tuning problem without breaking known physics. Whether they're correct remains uncertain, but they point toward a universe that continually rebalances itself, a dynamic equilibrium between emptiness and existence. When you zoom out, the philosophical implications carry as much weight as the math. The deepest truth here isn't an equation, it's a shift in perspective. The emptiness between stars isn't waiting to be filled, it's the framework that allows stars to be. Every atom vibrates against a background that never truly rests. The vacuum links the cosmic and the quantum, connecting the grand expansion of galaxies with the flicker of brief, unseen particles. And that connection invites the next question. If energy can surge briefly from the vacuum without breaking any physical laws, could that same principle work on a grander scale? Could a universe itself be the ultimate fluctuation, one that expanded before it could collapse back into balance? It's a radical thought, yet it follows directly from the rules of uncertainty. The more we study this empty realm, the more it behaves like the true substance of everything. What used to be dismissed as nothingness now looks like the engine room of reality, restless, unpredictable, but perfectly lawful. The vacuum isn't absence. It's the background note to the cosmic symphony, humming beneath every atom and every star. That hum leads us onward, because once scientists realized the vacuum is active, they began to recognize something even bolder. Under quantum mechanics, creation doesn't require a cause in the classical sense. The next step of our journey is to explore that loophole, the rule-bending feature of nature that lets existence momentarily appear from nothing, and in our case, never disappear again. The quantum loophole. Here, S where the rules of nature start bending into something that feels less like science and more like magic. Quantum mechanics says the universe doesn't run on certainties, it runs on possibilities. And at that level, the line between existence and non-existence isn't a wall, it's a blur. What we call nothing still trembles with probability. Even when there are no particles, no radiation, not even light, the uncertainty principle insists there's still motion. Energy can never be exactly zero because energy and time are linked. Fix one precisely and the other becomes undefined. That uncertainty cracks a tiny opening, a loophole, through which reality can sneak into being. This loophole sits in one of the simplest ideas in physics, conservation of energy. It says energy can't appear from nowhere, but quantum theory adds a twist. It can borrow energy as long as it pays it back fast enough. The briefer the existence of a fluctuation, the larger the lone nature allows. So a particle-antiparticle pair can spark into existence for an instant, then annihilate before anyone notices, leaving no debt. On the smallest scales, this happens relentlessly, and normally everything balances. But imagine a situation where that balance tips just slightly. If gravity enters the scene, those energy exchanges can become more than temporary sparks. They can seed entire worlds. Here's how the math plays its trick. Positive energy resides in matter and radiation. Gravity, by contrast, contributes negative energy because it binds things together. If the total sum of both ends up at zero, then the universe doesn't break any accounting laws by existing. It's like pulling money from one pocket and putting it in another. Nothing lost, nothing gained, just rearranged. In that balance lies the breathtaking implication. The universe didn't break the rules to exist. It found the one loophole that made existence legal. Physicists like Stephen Hawking described it plainly. The universe could be the ultimate free lunch, born from a perfect balance between matter's cost and gravity's credit. In that exchange, creation becomes a zero-sum masterpiece, an infinite structure powered by nothing owed. The concept found its most dramatic showcase around black holes. In the 197s, Hawking combined quantum theory with general relativity and found that black holes aren't completely black. Near their event horizons, pairs of virtual particles constantly appear. Usually, they vanish together, but if one particle falls into the black hole while the other escapes, the one that escapes becomes real energy, radiation. The black hole loses an equivalent amount of mass. This process, now called Hawking radiation, is a direct example of quantum fluctuations converting into tangible reality. Energy and particles appear, but the books still balance. The hole's mass drops, the radiation carries away the debt, and the laws stay unbroken. That same logic, applied to the early universe, creates a jaw-dropping possibility. If space itself can curve and stretch, then perhaps a quantum fluctuation large enough could inflate outward faster than it could collapse back. Cosmic inflation theory suggests something like that might have happened. A tiny fluctuation expanded exponentially, driven by its own energy density, until it cooled and stabilized as the space we inhabit. That event would look to us like a Big Bang, but from the quantum perspective, it was simply a fluctuation that didn't fade. No cause outside physics required, just the mathematics of fields behaving under uncertainty. Physicist Lawrence Krauss articulated the idea in bold terms, arguing that under quantum gravity, nothing is an absence but a state with the potential to produce space and time. Vacuum energies fluctuate, and those fluctuations can generate entire universes if the conditions allow. In that view, Our cosmos popped out of a quantum field exactly the way subatomic particles constantly pop in and out of vacuum, just scaled up beyond comprehension. Once inflation began, it amplified that microscopic event trillions of times over, freezing randomness into structure. Galaxies, stars, people. But as soon as that claim hit the public sphere, a new debate ignited. Critics said crosses, nothing, wasn't truly nothing. It presupposed the existence of quantum fields and physical laws. That's not zero, that's groundwork. Philosophers accused science of playing semantic games, but physicists countered that total absence is meaningless in measurable terms. They work with what can, in principle, produce measurable effects, and in that sense, the quantum vacuum is the closest thing to nothing our equations can describe. It isn't mystical, it's mandatory. Without it, the math of reality doesn't close. Let's step into that tension for a moment. At the human scale, nothing means total void. At the quantum scale, emptiness is just the lowest rung on the energy ladder. The difference isn't trivial, it's the entire reason we exist. When cosmologists draw diagrams of the early universe, they start not from true zero, but from a seething field with fluctuations too small to notice. Then, through inflation, those fluctuations were stretched across the cosmos. The patches of slightly higher density later became galaxies. The seeds of everything, including you and me, trace back to that restless quantum fabric. If that's not poetic, I don't know what is. Still, the loophole leaves a haunting question. Why do the laws of quantum mechanics and gravity exist at all? If they can spontaneously produce universes, then what establishes those laws in the first place? Physics answers how, not why. But within that how, we glimpse something profound, the possibility that existence is self-consistent. Once the framework exists, it generates its own realities without outside help. The universe could be what mathematicians call recursively self-defining, a system that bootstraps itself into being. That's dizzying, but it fits the data far better than any infinite regress of causes. Proof remains indirect, of course. We can't reproduce a universe in a lab, but we can simulate aspects of the process. Experiments in quantum optics show how vacuum fluctuations generate real photons in rapidly changing electromagnetic fields, a phenomenon called the dynamical Casimir effect. It's a small-scale cousin of cosmic creation, turning motion and empty space into measurable radiation. Each confirmation of that effect strengthens confidence that quantum indeterminacy genuinely produces energy under the right conditions. The loophole also explains why the universe's total energy could be zero, even though it contains unimaginable amounts of matter and radiation. Add up every particle, every burst of light, every gravitational well, and the grand total might balance perfectly to nothing. In that sense, the universe didn't come from nothing. It still is nothing, arranged in a more interesting form. Positive energy in matter and negative energy in gravity stay locked in eternal equilibrium, a cosmic seesaw where the fulcrum is the laws of physics. Some see this as demystifying creation, stripping it of wonder, but looked at differently, it amplifies wonder through logic rather than faith. A reality capable of generating complexity from mere probability rules is no less awe-inspiring than any divine gesture. The loophole doesn't kill meaning, it redefines it. It shows that something is the natural state once we accept that absolute nothingness might be impossible. Even voids must tremble, and from those tremors rise skies, mountains, and minds. But here's the lingering catch. If universes can form this easily, why don't we see new ones bubbling off around us? The answer lies in scale. Quantum fluctuations that large require extreme conditions, densities near the Planck limit, where our known physics teeters on breakdown. Those energies existed only at the very beginning, or deep inside phenomena we can't access, like black holes. So the factory of creation might be perpetually active beyond our comprehension, producing other universes beyond our cosmic horizon. And that idea brings philosophy full circle. The loophole proves that under existing laws, creation is possible without cause, yet it forces us to ask what counts as existence before those laws apply. Does a potential field without space or time qualify as something? Or does it hover in the same conceptual realm as mathematical truth, real but not tangible? Whatever the answer, the word nothing no longer feels accurate. The vacuum isn't a blank. It's a canvas already primed with the rules of composition. The irony is almost comical. We searched for the origin of everything and discovered that emptiness was never empty. Within quantum mechanics, cause and effect blur, beginning and ending overlap, and the universe becomes a self-contained loop of possibility. The loophole at its core isn't a cheat in the laws of physics. It is the law. Creation, it seems, is written into the uncertainty that keeps the cosmos alive. And yet, outside the labs and lecture halls, that conclusion stirs discomfort. Philosophers remind us that redefining nothing doesn't solve the conceptual puzzle, it sidesteps it. If science calls a vibrating field nothing, then what word is left for actual non-being? That question will ignite entire debates in the years ahead. For now, though, one thing's undeniable: nature's loophole works. It made a universe out of probability, and it continues to remake it every second. Because of that, our search must move beyond physics alone. The next step isn't about equations, it's about meaning. If scientists say physics explains creation, philosophers will always ask, creation of what exactly? And that clash, as old as curiosity itself, is where the story heads next. Philosophers push back. The moment physicists began using the word nothing in equations, philosophers felt an alarm bell ring. After all, nothing isn't a scientific term, it's a metaphysical one. In everyday language, it means complete absence. No matter, no fields, no laws. But when scientists like Lawrence Krauss or Stephen Hawking say the universe came from nothing, they're not describing absence. They're describing a physical state ruled by existing quantum laws. To a philosopher, that's cheating. It's like calling a blank canvas nothing when it's really full of potential waiting to be painted. This disagreement quickly escaped journals and landed in the public arena. Krauss argued that quantum mechanics alone can create a universe because virtual particles emerge naturally from the vacuum. No divine trigger required, just physics doing what physics does. But critics such as William Lane Craig and other metaphysicians countered that the laws of quantum theory aren't physical objects. They can't act or create without being instantiated in something. Nothing, they said, lacks the power to do anything. You can't get dynamics from non-existence. Their point draws from Leibniz's principle of sufficient reason, an idea 3 centuries old but still sharp as ever. It says everything that exists must have a reason for existing, some cause or explanation. If there were truly nothing, then there'd be no reason for something to appear instead. Nothing possesses no properties, no potential, no capacity to generate. You can't bake a universe when you have no ingredients and no oven. To philosophers, calling the quantum vacuum nothing is a sleight of hand, using new definitions to dodge an ancient paradox. Physicists reply with their own challenge. Why assume every event needs a classical cause? In quantum mechanics, events happen probabilistically without a defined trigger. Radioactive atoms decay spontaneously. Particles tunnel through barriers without classical permission. If micro-events can occur uncaused, perhaps the macro event of the universe's birth followed the same rule. For them, the sufficient reason is simply that the laws allow it. Existence doesn't need an external push. It's what happens when the math runs. And that's where the conversation collapses into 2 languages talking past each other. One side treats law as a description of patterns within existence. The other treats it as a potential governing structure that can't exist unless something exists to follow it. When Krauss says nothing, he means a pre-universe state where space and time have 0 expectation value, but quantum fields still obey fundamental rules. When a philosopher hears that, they think, then it's not nothing, it's a field, the exact opposite of nothing. Both are right within their frameworks, but they're addressing different questions. Physicists talk about how something might arise. Philosophers ask why anything can at all. The debate hardened in the 200s and never really cooled. Public discussions often turned personal, yet beneath the rhetoric sits a genuine confusion about language. Science reduces complex phenomena to models. Philosophy interrogates meaning and coherence. Physicists talk about fields. Philosophers talk about absence, as one commentator put it. It's not the same conversation. Still, each side needs the other. Physics describes reality's behavior, but philosophy guards the boundaries of definition, making sure words like nothing retain precision. Even Stephen Hawking entered the argument, claiming that because of gravity, the universe can and will create itself from nothing. His point: if gravity ensures the total energy of the universe is zero, then no external agent is required. Philosophers responded immediately: gravity isn't nothing, it's a property of space-time. The rules enabling creation still exist. To them, that's like saying a novel writes itself because grammar exists. Real writing needs something that chooses to use the grammar. Underneath the philosophical sparring lies a deeper emotional current. Scientists find elegance in self-contained explanations, where the universe is lawful and autonomous. Philosophers worry that by relabeling something as nothing, we lose depth, maybe even humility. The idea that existence needs no cause challenges the human instinct for meaning. It suggests there was no purpose, no plan, only probability. For thinkers in the tradition of Leibniz or Aquinas, that feels like erasing the very question their discipline was built to ask. But perhaps what looks like erasure is a kind of evolution. Even among philosophers, newer voices argue that nothing might be an incoherent concept. Maybe absolute non-being can't exist, not even hypothetically. If so, then debating whether the universe emerged from nothing is like debating whether a square circle could appear spontaneously. It's a false problem. In that reading, physics isn't redefining nothing. It's revealing that true nothingness isn't a possible state of affairs. Something always is, even if what is differs drastically from our intuition. Others take the opposite route. They insist that the quantum vacuum is a form of something precisely because it contains mathematical structure. Their concern isn't semantics, it's metaphysical consistency. If laws exist timelessly, what holds them up? Do the laws themselves require explanation, or do they exist necessarily? For some, that necessity points back to a grounding reality beyond physics, a metaphysical substrate, or even a divine rationality that ensures stability. For atheistic naturalists, that claim feels unnecessary. They counter that the laws simply are unchanging truths not contingent on anything. Round and round it goes, each side demanding the other justify the first link in the chain. It's a strange crossroads. We have equations predicting how something emerges from near nothingness, but no consensus about whether that scenario satisfies our instinct for explanation. The nothing of physics works spectacularly well inside experiments. The nothing of philosophy holds moral and existential weight. Each field defends a different kind of truth, one empirical, one conceptual. Bridging them might require a new vocabulary altogether, one that replaces opposites like being and nothing with relational terms such as potential and realization. Somewhere between those words lies a middle ground, a recognition that definitions evolve as knowledge grows. 500 years ago, vacuum meant pure emptiness because our tools couldn't detect fields or energy densities. Today, instruments measure the pressure of the quantum vacuum itself. Maybe the word nothing is following the same pattern, shrinking as understanding expands. Each discovery turns a once empty space into a new kind of fullness. Yet, as the arguments unfold in conferences and late-night podcasts, something quietly beautiful emerges. The debate keeps both wonder and reason alive. Scientists remind us that the universe could be self-consistent, that complexity can blossom without outside intervention. Philosophers remind us that explanation itself has boundaries, that logic alone can't furnish meaning. Together they form a dialogue as old as curiosity, the tension between describing how and asking why. In the end, maybe both are part of the same story. The cosmos could be lawful without being purposeless, emergent without being accidental. Calling a quantum field something or nothing may matter less than acknowledging our drive to understand it. We explore because ignorance feels wrong, yet that impulse, to chase the cause behind the cause, might be the universe re-examining itself through us. So the next time you hear someone say the universe came from nothing, remember that the phrase hides two very different visions. To the physicist, it celebrates a loophole where rules allow self-creation. To the philosopher, it's a warning that clarity slipped away when we blurred language with equations. Between them lies the space that makes both possible: thought, an activity born of something made from what looks like nothing. And that tension, unresolved and fascinating, opened the door to a new idea. Maybe reason itself is the next frontier of creation. Maybe understanding is what gives being its spark. Quantum gravity and the birth of spacetime. When science tries to peer behind the Big Bang, its language starts to break down. General relativity treats space and time as a continuous fabric that bends with energy. Quantum mechanics describes particles and fields vibrating on a fixed background of spacetime. The instant you ask both theories to work at once, at the universe's first fraction of a second, they explode into contradictions. Infinite densities, undefined times, diverging equations. That's the signpost reading. Our map ends here. But physicists don't stop at signs, they rebuild the map. Quantum gravity is that rebuilding effort. For decades, researchers have hunted for a theory that merges Einstein's smooth geometry with quantum theory's restless uncertainty. The goal isn't small. It's nothing less than explaining creation itself in consistent mathematics. Imagine replacing the singular point of the Big Bang with a process, a transition, a quantum event where spacetime crystallized out of a deeper reality. That's the promise of quantum gravity, a cosmos emerging not from a void but from its own quantum foundations. One branch, called loop quantum gravity, takes Einstein's equations and quantizes them directly. In this picture, space isn't continuous. It's woven from tiny, discrete loops, forming a network sometimes called spin foam. Volumes and areas come in smallest possible units, like pixels on the cosmic screen. When scientists run their calculations backward, the universe never shrinks to a singularity. Instead, density reaches a maximum, then rebounds. The Big Bang becomes a big bounce, a transition from a prior contracting phase to our current expanding one. There's no moment of nothing, only a change of direction. If true, that means the universe has no absolute beginning. It recycles through quantum compression and release. Another line of thought flips the question completely. Instead of quantizing space, it asks whether space is even fundamental. Could geometry itself be an emergent phenomenon? In recent years, theories of emergent gravity and gravity from entropy have taken shape. In these ideas, spacetime behaves like a large-scale statistical effect of microscopic quantum information. Just as temperature arises from countless molecules bumping around, gravity might arise from bits of information striving toward equilibrium. One approach, developed by Professor Ginestra Bianconi, treats gravity as a consequence of quantum relative entropy, a measure of how information differs between quantum states. From that framework, gravity isn't a force but a bookkeeping of information flow. The mathematics astonishingly produces Einstein's equations and even forecasts a small positive cosmological constant, the same gentle push we observe as dark energy. That's more than clever coincidence. If entropy can give rise to spacetime, then the laws governing expansion might be inevitable patterns of information balancing itself. Nothing would then mean no distinguishable information, and once distinctions appear, geometry appears too. Existence emerges as the universe starts telling itself apart. Meanwhile, a team at Aalto University recently proposed a new quantum field model of gravity compatible with the standard model of particle physics. Instead of treating gravity as curvature, they describe it as four interrelated quantum fields, mirroring how we describe electromagnetism or the nuclear forces. The benefit is consistency. The mathematics stays stable at high energies, avoiding infinities that plague earlier models. And when they test the equations against cosmic data, they yield a positive cosmological constant, nearly identical to what astronomers measure. It's the first concrete sign that quantum mechanics and cosmology could live in one coherent theory. What's striking about these advances is how they redefine beginnings. Each model replaces creation ex nihilo with transformation, order arising from quantum chaos, structure forming as probabilities collapse. Instead of a single cosmic spark launched from nowhere, we get a continuous self-organizing process. Reality, in this view, bootstraps itself. Quantum laws generate energy. That energy defines geometry. Geometry creates time. The moment of birth isn't an explosion. It's a phase change, like water freezing into ice, except the substance solidifying is spacetime itself. For a while, these ideas seemed purely theoretical, but technology is catching up. New gravity wave observatories and quantum interferometers are starting to look for signatures of spacetime discreteness or entanglement. If space is made of quanta, its tiniest vibrations should imprint subtle patterns on gravitational waves. Detecting those would confirm that classical geometry truly dissolves at the Planck scale. The search has begun, blending cosmology with quantum optics, frontier physics working across an unimaginable gulf of scale. The emotional weight of this research often sneaks up on the scientists doing it. Many admit that what drew them in wasn't the equations. It was the sense of standing at the crossing between existence and nothingness. Quantum gravity is in some ways our most disciplined form of wonder. It tries to explain how the laws themselves could arise naturally, without invoking anything outside the system. If successful, it would turn the universe from a miracle into a proof, yet the feeling it inspires is still awe. Picture the early universe as a fog of probability, each fluctuation a warped potential spacetime. One fluctuation reaches a threshold, geometry condenses, and time begins to flow within it. To observers like us, that event looks like a sudden beginning. But from outside, a notion we can barely define, it's just one more moment in a timeless quantum configuration. The Big Bang wasn't an explosion in space, it was the emergence of space. Everything since then, galaxies, atoms, thoughts, are ripples propagating through that newly born medium. Quantum gravity also revisits an ancient philosophical idea. The universe might be self-necessitating. The equations yield a non-zero energy vacuum as their most stable state. In plain terms, a state of nothing is unstable. It naturally transitions into something. Existence, then, isn't an accident. It's the path of least resistance under the logic of quantum fields, a phenomenon not of chance but of inevitability. The cosmos exists because non-existence can't hold itself together, because stillness, at the deepest level, is impossible. Nothing dissolves into being the way silence collapses into sound. Of course, physicists express that idea in cautious language. They say the vacuum isn't symmetric under total absence, that the ground state decays into spacetime. But the meaning behind the math sounds hauntingly close to inevitability. There may have never been a choice to begin or not begin. The laws, once defined, ensure their own manifestation. That reflects back on us in surprising ways. If spacetime is a product of quantum information, then consciousness, another information process, might share deep kinship with the universe's structure. It isn't mysticism, it's pattern recognition. The same mathematics that births geometry also describes entangled mental states in quantum computing labs. At the deepest level, reality might be a computation running on the hardware of pure possibility. Still, for all its sweeping beauty, quantum gravity humbles us more than it empowers us. Every model solves one paradox only to uncover another. Replace the singularity with a bounce. Then where did the previous phase come from? Treat gravity as information. Then what generates that information? Each answer births a fresh void to fill. Yet that endless recursion feels oddly fitting. Maybe the cosmos isn't a question with an answer at all, but a process that forever circles its own logic, transforming question into consequence. For now, we measure clues. We analyze cosmic microwave background data for signatures of pre-Big Bang structure. We test whether black holes leak quantum information as theory predicts. We build lasers precise enough to detect spacetime's quantum grain. Each discovery trims the borders of ignorance. But at the core remains that slender truth. Every one of these theories points to an origin woven from the quantum fabric itself. Not created from outside, not imposed from above, born from within. Standing under a clear night sky, that thought can hit harder than any equation. The stars aren't distant lights scattered in an empty void. They're sparks flickering across an ongoing field of creation. Even now, spacetime still stretches, still calculates its next moment from probabilities engraved at its birth. The universe doesn't sit on nothing. It is the unfolding of nothing into form. And maybe that's the quiet revelation hidden in all this calculus. Reality might not need a first cause because existence is what nothing does when it can't stay still. Spacetime blooms out of quantum law the way foam rises from waves, inevitable, intricate, and beautiful beyond measure. Math can show how it happens. Only wonder reminds us why we care. So when physicists talk about quantum gravity uniting the very small and the very large, what they're truly describing is a bridge, a place where logic and awe shake hands. The numbers imply that the universe built itself from the fabric of probability. The feeling implies that we're witnessing creativity woven into the law of nature. And that leaves one final question lingering like cosmic background radiation. Even if math explains how, do we ever stop asking why? Multiverse and vacuum transitions. If a single quantum fluctuation can create one universe, what's to stop it from creating many? That's the question that's kept cosmologists awake ever since they realized how fast the infant cosmos must have expanded. Inflation, the idea that space itself ballooned exponentially in a split second, solves a lot of puzzles. Why the universe looks uniform in all directions, why its curvature seems flat, why tiny density variations became the seeds of galaxies. But inflation also comes with a wild side effect. If it's possible once, it may be happening everywhere forever. Alan Guth, the physicist who first proposed inflation, noticed that quantum uncertainty would make it uneven. Imagine patches of space where the inflating energy decays and stops. That's where baby universes like ours appear. But other patches keep inflating, stretching faster than they can fade. Over time, you get an endless froth of inflating space dotted with bubbles, each cooling into its own universe. Our cosmos could be just one bubble in an infinite multiverse still bubbling right now. In that picture, everything means everything that can happen, happening somewhere. Inside each bubble, physical constants could differ. One might form stars quickly, another might collapse before atoms ever combine. Maybe most universes flash and vanish within microseconds. We live in one stable enough to ask why. That turns the old fine-tuning problem on its head. Life didn't require miraculous settings. We just observe the one bubble where those settings happen to allow observers. It isn't destiny, it's statistics. The theory sounds extravagant, yet its foundations are pure physics. Inflation fields obey quantum rules. Their fluctuations are random. Given infinite time and volume, every configuration occurs. The challenge is evidence. We can't step outside our bubble to check, but scientists hunt for scars left from past collisions, slight ripples imprinted on the cosmic microwave background. If two bubbles ever touched, their interaction could leave circular patterns or polarization anomalies in the relic radiation from the Big Bang. So far, data from Planck and other satellites show no decisive hits, but new computer simulations suggest what to look for: subtle swirls of polarization that could betray ancient crash sites. Spot 1. and we'd have the first observational hint of other universes brushing against ours. Meanwhile, another approach, rooted in string theory, pushes the idea even further. In that framework, reality may have more than the familiar 4 dimensions. Tiny vibrating strings exist in 10 or 11 dimensions, and the extra ones are curled up in complex shapes called Calabi-Yau manifolds. Each shape corresponds to a set of physical constants, different masses, forces, even numbers of particles. When theorists count possible shapes, they find not hundreds but trillions upon trillions. Every configuration could describe a unique universe, a vast landscape of possibilities. The multiverse, in this sense, isn't speculation. It's a mathematical consequence of the equations used to unify gravity with quantum physics. Physicists nickname it the string landscape, and our universe is one valley within it, resting in a particular state of vacuum energy. But here's where vacuum transitions come in. Quantum field theory allows different vacua, different baseline energy levels, to coexist. Under rare conditions, one vacuum can tunnel into another, like a ball finding a lower valley through a hidden pass. When that happens, the transition releases energy that forms a new bubble of space expanding at near light speed. If this occurred early in cosmic time, it could explain not just a single origin but repeated births of universes, each with slightly adjusted parameters. Think of reality not as one expanding balloon, but as a field of soap bubbles, each growing, bursting, and spawning new ones endlessly. It's breathtaking and terrifying at once, because if vacuum decay happens once, nothing stops it from happening again. Physicists even calculate a faint possibility that our current vacuum isn't the absolute minimum energy state. Somewhere in the far future, or in some remote region, it could tunnel again, triggering a new bubble that annihilates everything it touches. The odds are vanishingly tiny on human timescales, but in the mathematics of eternity, tiny doesn't mean impossible. That vision transforms how we think about beginnings. Instead of a single creation event, the universe becomes part of an eternal process of emergence. No start, no edge, just transitions between quantum states. Inflation ends locally but continues globally, a cosmic fractal generating infinite versions of reality. Some cosmologists call this eternal inflation. Others see it as a bridge to the full-blown multiverse. Either way, it means the Big Bang might have been just our local spark. Adding another layer, quantum interpretations like many worlds extend the idea inward, into quantum measurement itself. Every time a quantum event occurs, all outcomes happen, branching reality into countless copies. That version of multiverse doesn't spread through space. It proliferates through possibility. Combine it with cosmic inflation, and you get hierarchies of branching, universes spawning universes, each containing infinite forks of quantum history. Somewhere else, every decision unmade plays out. Somewhere else, physics itself chose another role of constants. Skeptics call this untestable, bordering on philosophy. And maybe they're right for now. But theory and observation keep tightening their dance. Data from the Laser Interferometer and upcoming gravitational wave missions might detect faint signals from primordial inflation, indirect fingerprints of those bubble births, even without proof of other universes. Confirming the exact energy scale of inflation would inform how plausible that eternal mechanism is. To scientists like Andre Lind, one of inflation's founders, the multiverse isn't extravagance, it's inevitability. The equations simply don't stop at one universe. In his view, existence itself is a self-reproducing process, perhaps never destined to end. A cosmos that can create itself once is bound to do it again and again in every possible way. It's a reality where the improbable isn't rare, it's mandatory. But beyond equations, the multiverse stirs something deeply existential. If infinite universes exist, our story occupies a vanishing fraction of them. That idea can feel freeing or crushing. On one hand, nothing we do alters the whole. On the other, every version of us does exist somewhere, repeating or diverging endlessly. In that light, significance isn't about uniqueness. It's about witnessing one thread in the endless tapestry. Philosophers have stepped into the discussion, too. Some argue the multiverse offers a natural resolution to the anthropic puzzle. We observe conditions suitable for life because we couldn't exist in any universe where they were. Others counter that such reasoning hides a lack of deeper explanation, a retreat into probability. But probability itself may be the ultimate creative force, the same quantum randomness scaled up to cosmic proportions. Just as a single fluctuation birthed our universe, an infinite array of fluctuations could generate them all. Recent years brought digital reinforcements. Supercomputer simulations now model inflationary bubble collisions, track how different constants change nucleosynthesis, even predict galaxies forming under alternate physical laws. What emerges is astonishing. Most universes would look sterile, with no chemistry beyond hydrogen and helium. A tiny subset with delicate balances of forces produce complexity. Among those rare few, ours sits right where it needs to. Whether that's coincidence or design depends on which question you're asking. In practical terms, these theories sharpen our understanding of dark energy and vacuum stability. The same calculations that predict bubble universes also dictate how our own vacuum behaves, including whether it can decay. So studying the multiverse isn't escapism, it's safety research on existence itself. Knowing the energy thresholds could tell us whether our reality is permanently stable or just temporarily calm. Still, step back from the equations and there's awe hiding behind every term. Picture it, an endless expansion of bubbles, each unfurling its own spacetime, each carrying different constellations that will never share light. Somewhere within that incomprehensible foam are versions of you, galaxies built on unfamiliar chemistry, sunsets the color of unimagined spectra. Somewhere else, physics never allowed stars, only darkness stretching forever. And all of it, from infinite brilliance to infinite emptiness, born from the same simple rule: the vacuum can't stay still. So what do we make of that? A universe that breeds infinities might make ours feel small, but it also connects everything through one principle: creation as a recurring property of reality. The same quantum laws that let our cosmos escape nothingness don't know when to stop. They ripple outward endlessly, writing infinite possible stories on the blank page of potential. And maybe that's the ultimate revelation. Eternity isn't about time lasting forever. It's about creation never running out of room. If each bubble universe is another try, another permutation of how something can be, then existence itself might be the multiverse's language, spoken in endless dialects of physics. We just happen to live in one verse of the poem. If that's true, then our beginning wasn't singular. It was one note in an eternal chorus. Somewhere beyond the cosmic horizon, the song goes on. And that leaves us here, listening for echoes, wondering whether we're a miracle among many, or just one verse reciting itself into new universes forever. Dark energy and the universe's future. When astronomers discovered the universe's accelerating expansion, they realized they were staring at the most powerful force no one could see. They called it dark energy, but the name hides how little we know about it. It's not dark like night. It's invisible, smooth, and everywhere. It doesn't pull, it pushes. It's the quiet pressure stretching the cosmos wider every second, the legacy of that same cosmological constant Einstein tried to bury. And yet, despite decades of observation, dark energy remains the most mysterious majority in existence. Right now, about 70% of the universe's mass energy budget is this invisible component. The rest is mostly dark matter, about 27%, while ordinary atoms make up a mere 5%. That means everything we can see, from galaxies to you breathing right now, is only a trace element in a reality dominated by something we barely grasp. It's unsettling, but also liberating. The universe is stranger than human intuition ever dared guess. Let's rewind to when this revelation struck science like lightning. In the late 199s, two teams, the Supernova Cosmology Project and the High Z Supernova Search Team, used Type Ia supernovae as cosmic mile markers. These explosions shine with consistent brightness, so astronomers can measure their distances by comparing intrinsic and observed light. What they found defied expectation. Faraway supernovae looked too faint, implying they were farther than a decelerating universe would allow. Gravity wasn't slowing expansion down. It was losing ground to something pushing outward. To fit the data, cosmologists revived Einstein's lambda, this time interpreting it as vacuum energy, a constant force woven into space itself. In one equation, lambda adds a persistent outward acceleration unrelated to matter or radiation. With that term reinstalled, the cosmic puzzle clicked neatly together. Observers suddenly realized that emptiness itself dominates cosmic behavior. Space expands not because objects move through it, but because the fabric of reality stretches between them. Every proton, every atom, every galaxy drifts farther apart, carried by space's own restlessness. What happens next depends entirely on dark energy's temperament. If it stays constant, the cosmos faces a long, cold retirement. Galaxies beyond our local group will slip beyond visibility as cosmic expansion outruns every beam of light. Stars will burn out, black holes will slowly evaporate, and the sky will fade to emptiness. Astronomers call it the Big Freeze, a timeless drift into darkness and silence. But not all models guarantee peace. If the repulsive energy intensifies with time, something theorists label phantom energy, its pressure could eventually overpower every force in nature. First, it would tear apart clusters, then galaxies, then atoms themselves. Even space's quantum fabric could rip in a final convulsion, the Big Rip. According to current measurements, this scenario is unlikely, but our margin of error is large enough that no one can declare it impossible. The end of everything might still be written in decimals we haven't measured. The fascinating alternative lies between those extremes. Some physicists suspect dark energy evolves slowly, transforming as the universe ages. These running vacuum models suggest that lambda isn't truly constant but depends on the Hubble rate, the cosmic expansion speed. As the universe changes, so does the vacuum's energy density, allowing a dynamic feedback loop that could smooth fine-tuning problems. In that picture, dark energy diluted the early universe less efficiently, then stabilized to the value we see now. Future measurements may catch it drifting again, a cosmic heartbeat echoed in redshift data. New instruments are hunting for that pulse. The Dark Energy Spectroscopic Instrument DAISY is mapping millions of galaxies to trace expansion history with unmatched precision. Euclid, launched by the European Space Agency, scans deep space for subtle distortions in galaxy shapes caused by gravitational lensing, a direct probe of how dark energy reshapes geometry. And upcoming surveys like Vera Rubin's LSSD will track the flicker of billions of supernovae, timing how quickly they recede. Each dataset narrows the possibilities, confronting theory with reality in slow motion. If even a slight deviation from constancy appears, it could point to new physics, perhaps a rolling field, perhaps the whisper of quantum gravity. Meanwhile, theorists test whether dark energy connects to earlier questions of vacuum energy. One trail leads back to those staggering quantum calculations, predicting a vacuum density far too high. Maybe the observable cosmological constant we see today is just the net residue after vast cancellations among fields, a trimming left by deeper symmetries. Some propose that supersymmetry, if ever confirmed, might neatly zero gravity interaction energies, explaining why space appears nearly weightless. Others invoke vacuum decay dynamics, where energy stored in false minima slowly drips away, leaving behind the delicate residue we observe as acceleration. Each explanation reads like a page torn from cosmic bookkeeping, the universe balancing its books down to 30 decimal places. But dark energy isn't only a number in equations, its destiny made quantitative. As expansion accelerates, cosmic distances grow exponentially. In a few tens of billions of years, light from any external galaxy will no longer reach us. Astronomers of the far future, trapped within the Milky Way remnant, will gaze into a blank sky, unaware that other galaxies ever existed. Cosmology itself will become impossible. The evidence of origin will fade, leaving only isolated stars adrift in perpetual twilight. The thought is melancholy, reality erasing its own diary. Yet in another sense, dark energy gives existence its grandeur. It proves that even the void isn't inert, that creation continues in silence. Each cubic meter of space carries roughly 5 × 10⁻⁻10 joules of energy, tiny per unit, infinite in total. Multiply that by the observable universe, and emptiness outweighs everything. Nothingness rules by majority vote. Ironically, those whispers of vacuum are the same phenomenon that may have launched the cosmos in the first place. The energy filling space today might be a faded echo of the inflationary driving force that blew the early universe apart. Both arise from the vacuum and both dictate expansion, bookends of cosmic history separated by billions of years. The universe may be living through a long second wave of creation, slower but unstoppable. Still, one unsolved question keeps physicists restless. Will dark energy remain uniform forever? Dacey's preliminary data hint at possible evolution, a subtle tilt suggesting that the cosmological constant could be more dynamic than once thought. If confirmed, we might be seeing the first evidence that space itself is adapting, its tension adjusting as galaxies thin out. That would blur the line between geometry and substance even further. The vacuum may not just host existence, it may respond to it. Thinking about that reshapes the emotional landscape more than the math. Everything humanity has ever known fits inside a tiny sliver of time when galaxies are visible and stars still burn. We live during an age of cosmic clarity, a brief window between primordial fog and ultimate blankness. Billions of years from now, the sky will close, and all memories of expansion will fade into local myth. We happen to exist at the one moment when the universe lets its story be read. So when cosmologists chart dark energy's curve, they're not only predicting the end, they're preserving knowledge before the curtain falls. And that effort loops us back to an earlier paradox. The same quantum vacuum that could birth a universe also decides its fate. The nothing that became everything continues to dictate what everything will become. Whether lambda drifts, oscillates, or stays steady, its quiet rule tells us something profound. Emptiness isn't an afterthought. It's the architect of both beginning and destiny, sculptor of time's arrow. The cosmos doesn't expand into nothing, it expands because of it. That's the ultimate irony written in starlight. The fabric that looks empty carries the power to end the show. And as we follow that accelerating drift outward, maybe that's the real cosmic lesson, not despair but acceptance. Creation isn't a single event. It's a process still unfolding in the spaces between galaxies, between atoms, between moments. The void that seemed lifeless is the pulse of eternity itself, quietly stretching, 1 second wider than the last. The paradox of nothing. So here we are, after tracing cosmic history from the first spark to the quiet breath of dark energy, standing before the same riddle we began with. If the universe can arise from a quantum fluctuation, if the vacuum hums with energy, if laws exist to make that possible, then what exactly do we mean by nothing? Because the deeper we dig into physics, the less convincing the concept becomes. The nothing of modern science looks suspiciously like something wearing an invisibility cloak. Philosophically, nothing means non-being, no space, no time, no rules, but physics can't even define a state without rules. Every equation assumes some framework where numbers mean something. Remove that and calculation collapses. So when scientists describe a vacuum, they imply structure. A network of fields, a set of symmetries, maybe even probability itself. That's not absence, it's groundwork. The paradox is that to model nothing, you already need something capable of modeling. Maybe the real root of reality isn't matter or energy, but law, the underlying relationships that remain when everything else vanishes. Those laws don't take up space or time, they simply are. And if those laws are stable, then a universe obeying them may be inevitable. Some physicists whisper this half-jokingly. Perhaps nothing is unstable. Maybe the calmest possible state naturally decays into existence. Quantum gravity theories hint at exactly that. A perfect zero vacuum would constantly fluctuate because even zero has uncertainty. Try to freeze reality, and it shakes itself awake. That idea reframes creation entirely. The cosmos might not have begun with a choice or a miracle, but with inevitability. Like water finding the lowest point, existence could be the only configuration that satisfies its own equations. Non-existence can't balance itself. Existence can. In that view, universes aren't extraordinary. They're the default outcome when mathematics gets restless. Still, the human instinct rebels. We ask, but where did the laws come from? It feels unsatisfying to treat physics as self-existing. Yet maybe that question hides a category error. Laws of nature aren't objects that need a shelf to sit on. They're descriptions of regularity. If those regularities are timeless, then craving an earlier cause may be as meaningless as asking what's north of the North Pole. The question dissolves once we grasp that time itself is part of the system, not a stage behind it. These reflections drag science into philosophy's oldest territory, being versus non-being. At first glance, they seem mutually exclusive, but quantum mechanics blurs borders for a living. A particle can exist in superposition, both here and not here until measured. Maybe the universe itself began in a similar state, potentiality suspended between being and nothing, collapsing into reality the moment its own laws allowed consistency. That isn't mystical, it's symmetry breaking on a cosmic scale. There's another angle. Maybe nothing was never absolute but relational. We define emptiness only relative to something more. Early in the universe, density and temperature were nearly infinite, yet compared to even earlier Planck-time froth, that hot plasma might have been its own version of nothingness, smoother, quieter, almost uniform. Each era's nothing becomes the next era's something. In that sense, creation never stopped. It just keeps redefining emptiness step by step. Quantum cosmology reinforces this continuum. Some models predict that what we call the Big Bang wasn't the first moment, but a transition from a prior vacuum state, a quantum tunneling event through spacetime's energy landscape. As one vacuum decays into a lower energy version, expansion ignites. From outside, it looks like birth. From within, it's just physics moving from one equilibrium to another. Nothing exceptional, unless you're inside the bubble watching galaxies form. What this means philosophically is staggering. Perhaps you can't have true nothingness at all, because even emptiness must obey probability. The universe, then, is probability made visible. Everything that can happen eventually manifests somewhere along possibility's continuum. Nothing becomes shorthand for zero probability events, things that simply never manifest. But if the probability of existence is non-zero, then across infinite opportunities, it's guaranteed. Reality isn't just possible, it's statistically mandatory. Such logic doesn't erase wonder, it deepens it. Because we find ourselves as conscious beings within that mandatory existence, thinking about law and logic as if we were separate from them. We're the universe's way of reflecting on its own loophole, a feedback loop of curiosity. Each equation we write and question we ask is the cosmos examining its blueprint and asking, why this design, not another? The more answers we find, the more the question regenerates. Nothingness, it turns out, might be creativity's ultimate disguise. And yet, for all our mathematical triumphs, we still wrestle with hesitation. Part of us longs for purpose beyond mechanism, for meaning that isn't reducible to probability. That longing doesn't vanish under data, it coexists with discovery. Maybe the real paradox isn't scientific at all, it's psychological. We look for intention in a universe that may simply be consistent. When physics says existence requires no cause, we quietly wonder if meaning can survive that independence. There's room for mystery even in rigor. Some researchers suggest that physical law itself could be emergent, that consistency, symmetry, and causality evolved from deeper statistical behavior. In that picture, the laws weren't pre-written, they self-organized as stability outcompeted chaos. Then our question morphs again. The universe didn't come from laws or from nothing. It came from possibility sorting itself into order. A hierarchy of nothings collapsing until one version holds. And maybe that's what draws so many thinkers, scientists and philosophers alike, back to the edge of meaning. Because behind every formula lurks an emotional realization. We're built from the same vacuum energy we once called void. Our atoms condensed from fluctuations in fields that never rest. We are, literally, organized nothing looking back at its own potential and calling it the sky. So when you stand under that sky, remember the absurd chain of reasoning that got you here. The power tearing galaxies apart is the faint residue of a vacuum that couldn't stay still. The same quantum trembling that forbids perfect emptiness produced your heartbeat. Existence may not need justification, yet it carries an intricate coherence that feels almost deliberate. And maybe that's what all really is. The recognition of order without author, harmony without composer. In the end, the phrase "something from nothing" might be misleading. We didn't come from nothing, we came through it. Through a stage that looks empty only until you learn how to listen. Beneath the silence of space hums the energy that birthed all things, steady and eternal. And as science edges toward uniting quantum law with cosmic history, it keeps returning to the same revelation. Nothing was never nothing. Maybe nothing is the universe's favorite trick word, a placeholder for all we've yet to understand. Because when every possible definition blurs, what remains is pure wonder, the sense that existence, against every intuition, makes sense by virtue of simply being. We've come full circle to where physics and philosophy meet, staring into the vacuum that started it all. And at that border, where equations reach silence, you can almost hear the echo. Maybe nothing was just waiting to become surprised by itself. All at the edge. We've traced the story from the impossible silence before the Big Bang to the quiet hum of the vacuum that still drives expansion. And somehow we end up right where we started, face to face with mystery. After all the equations and cosmic surveys, the question remains as haunting as ever. Why does reality bother to exist? Maybe no theory can outrun that question. Maybe it isn't meant to. Because what begins as physics always lands in wonder. Think about what we've learned. Every atom, every sunrise, every heartbeat is built from the same restless fields that once pretended to be nothing. The vacuum never stopped creating, it only slowed to a pace we can survive. In that sense, creation isn't a past event, it's the ongoing habit of the universe. Space keeps stretching, particles keep flashing in and out, and somewhere within those probabilities, awareness appears and asks what it all means. We are the loophole made conscious. And there's beauty in that circular truth. The universe doesn't seem designed for comfort. It's balanced on impossible numbers that could have been otherwise. Yet here we are, equipped with eyes sensitive to the faint afterglow of its birth, minds capable of writing down its laws. Out of uncertainty came pattern. Out of apparent emptiness came the capacity to contemplate emptiness. That's not an answer, it's a privilege. Science, for all its precision, records only the how. It sketches trajectories of galaxies, measures ripples in primordial light, charts the energy of the void. But behind each formula sits the quiet astonishment of being able to ask questions at all. Every discovery about the vacuum's power doubles as a mirror. It shows us the structure of reality and the structure of curiosity itself. Maybe that's the universe's most intricate feedback loop. Consciousness emerging from quantum laws, then turning around to decipher the laws that made consciousness possible. Somewhere in that interplay lies meaning, or at least the nearest thing to it we can grasp. Physics reveals that nothing stable can ever be truly empty, even zero quivers. Philosophy reminds us that explanation without wonder is hollow. Blend them, and you get a portrait of existence that's both logical and luminous. The cosmos doesn't require a beginning in the human sense. It flourishes because non-existence can't hold still. Being is the simplest form of motion. And so the phrase "something from nothing" feels less like triumph and more like confession. We once thought nothingness was silent. Now we know it hums at the root of all sound. We once pictured creation as an act. Now we see it as a condition. Between probability and perception stretched a universe, and within that stretch, life learned to notice. If you followed this story from the first whisper of quantum foam to the accelerating drift of galaxies, you've walked the longest known circle in science, the one where explanation turns back into awe. Perhaps that's the real purpose of understanding, not to untangle every thread, but to recognize the tapestry while it's still being woven. Look around tonight, the faint starlight crossing billions of years, the black intervals between. Both are part of the same unfolding equation. Darkness isn't absence, it's the negative space that lets creation breathe. The same vacuum that could, in another fraction of eternity, start again somewhere else. Maybe it already has. So we end here, standing quietly at the edge of knowledge, staring into nothing that's alive with possibility. Maybe we'll never uncover a final cause, but that doesn't lessen the feeling that the universe is trying through us to understand itself. All the data, all the theories, all the cosmic background noise amount to one message echoing through time. Nothing was never empty. It was pregnant with everything. And maybe that's the only true revelation we get. The void didn't need a reason, it needed time. Given enough of it, even nothing learns how to glow. If that idea stirs you, the thought that we're made of curiosity rising out of the vacuum, stay with it, because every question keeps the cosmos awake. Subscribe, join the community of seekers who find wonder in the simplest truth. Existence persists, and that's miracle enough.